Welcome back. In this video, we'll take a look at the potential of solar energy. Solar energy is the most flexible and fastest growing technology of electricity generation in the world. Photovoltaics has become the cheapest form of electricity generation in most parts of the world. So the learning objectives are again the same. Understand the energy chain concepts in which solar energy can be used and calculate and analyze the important performance metrics of a photovoltaic system. The conversion efficiency, the energy yield, the capacity factor, the surface power density, the carbon footprint, the carbon CO2 emissions and the energy payback time of a PV system. And to be aware of the pros and cons of photovoltaics. The solar irradiance is the primary energy source, of course. And using semiconductor materials like silicon, the light incident on the device can be directly converted to electricity. So photovoltaic modules based on these semiconductor materials convert the solar light incident on the panels into electricity that is collected, locally distributed, consumed or stored or transported to other end consumers. In thermal solar, the solar radiance is converted in usable heat. Like this, a solar collector that operates on the principle of absorbing solar radiation and converting it into thermal energy, heat, to heat a working fluid, typical water or antifreeze. The fluid circulates through the pipes and the thermal heat can be either stored or used. We will go in the exercises in more detail into this technology. In addition, solar energy can be converted into chemical energy using the photosynthetic process. Sunlight converts water and carbon dioxide into biomass. This type of bioenergy will also be discussed in the exercises following this video lecture. But in this video we'll focus on the photovoltaic solar energy. As discussed in the Sustainable Energy Systems MOOC, photovoltaics is currently the fastest growing energy technology in the world. Let's look into the primary energy potential, the system efficiency and the energy yield of typical photovoltaic systems. The primary energy source is the solar irradiance incident on planet Earth. Here I introduced the solar irradiation H. This corresponds to the total amount of solar energy accumulated on a unit surface area over a full year. It has the unit of kilowatt hours per square meters per year. The power density of solar radiation per unit is given by the irradiance G, which is expressed in watt per square meters or kilowatt in square meters. The annual solar radiation H is determined by the integration over the irradiance G for a full year. Here the annual radiation map of the world is shown. The distribution of the annual solar radiation is primarily driven by the Earth's spherical shape. It's 23.5 degrees axial tilt in reference to the Sun and the atmospheric conditions. The highest values for the annual radiation can be found around the equator, whereas the lowest values can be found towards the poles. The annual solar radiation varies therefore from 800 up to 2,800 kilowatt per square meters per year. The solar energy incident on planet Earth accumulated over 1 hour equals the primary energy consumption of humankind for 1 year. This demonstrates the amount of solar energy available. Often the irradiation is also expressed in the number of equivalent sun hours. In this graph you see the typical solar irradiance G over a single day. The total solar energy incident is the surface under this graph. 1 equivalent sun hour is defined as the total radiation of 1 kilowatt hour received on a square meter per day, or in other words 1 hour of the standard radiation conditions GAM 1.5 of 1 kilowatt per square meters. With other words, if we divide the solar radiation of a day by 1 kilowatt per square meters, we get the number of sun hours per day. With other words, if we divide the solar radiation of a day by 1 kilowatt per square meters, we get the number of the sun hours as shown here by the rectangle square. If we consider the global radiation map, the average number of sun hours varies from 7.5 equivalent sun around the equator down to 2 equivalent sun hours at the poles. A photovoltaic system consists of the photovoltaic module that converts the sunlight into a DC current and voltage. Using power electrical conversion components like an inverter, the DC current and voltage can be converted into an AC current and voltage to supply the appliance connected to a local AC circuit. The excess solar electricity not consumed can be transported using the AC grids to another end consumer. The efficiency of the system is determined by the conversion efficiency from the sunlight into electricity of the PV modules and the conversion efficiency of the inverter. For simplicity, we assume the typical conversion efficiency of an inverter 90% here. The conversion efficiency is defined as the generated power at a certain time t divided by the amount of solar light power incident on the module at the same time t, which is equal to the product of the surface of the PV module and the solar irradiance at time t. Similar to wind turbines, the conversion efficiency of PV modules depends on the operation conditions, like the irradiance, logically, and the temperature of the module as well. The higher the irradiance, the larger the efficiency, and the higher the temperature, the lower the efficiency. For simplicity, we show here that the conversion efficiency is constant. In Module 3, we will go more in detail how the efficiency depends on operation conditions. Similar to the wind turbines, PV modules have a rated power, referred to as the nominal power of the modules. This is the power a solar panel delivers under standard test conditions, which means standard test conditions, the incident irradiance, G, is 1000 watts per square meters or 1 kilowatt per square meters. The module is at an operation temperature of 25 degrees Celsius, and the spectral shape is the so-called air mass 1.5 spectrum. We will explain that in Module 3. The current commercial PV modules based on the crystalline silicon PV technology, which is the dominant technology, have a conversion efficiencies nowadays of 22 to 25% under standard test conditions. The fundamental losses of PV modules are thermodynamic losses, very fundamental losses there, optical losses like the reflection and the shading by contacts, electrical losses like the resistance and the reconfirmation of the charge carriers, and the spectral mismatch of the semiconductor spectral response, resulting in thermalization of absorbed photons at high energy, and the inability of low energy energetic photons to absorb in the infrared. Let's assume we have commercial modules with a size of 2 square meters, which is getting close to the real modules available nowadays. Taking the typical efficiencies of 22 to 25%, the nominal output of these modules would be 440 to 500 watt peak. The peak stands for the fact that the module is operating under standard test conditions. What is the energy yield of a PV system? Note, I will use a simplified picture here. I do not consider the orientation of the modules, the dependence of efficiency on the irradiance and temperature, as I mentioned before, but also the shading and soiling losses of the modules. The yield is then the integration of the power output over the time period of interest, like a full year, where the power output is equal to the multiplication of the area of the PV system, the modules, and the inverter efficiencies and the irradiance G. In this simplified picture, the efficiencies are considered to be constant and the yield can be simplified as the multiplication of the area's efficiencies and the annual radiation age. If you insert the irradiance of the standard test conditions into the equation, the expression can be rewritten in the product of the nominal power and the equivalent number of sun hours in a year. On average, over the surface of planet Earth, the daily irradiation is equal to 4 up to 5 equivalent sun hours. Let's consider the yield for a single day of a typical 2 square meters photovoltaic module, and that will then generate 1.8 to 2.5 kilowatt hours per day if we plug in the numbers. The capacity factor for photovoltaics is again the delivered yield over a year divided when the module would have been operating under the nominal power for the full time. As for simplicity, we consider the conversion efficiency to be constant. This equation can be simplified to the ratio between the annual radiation and the rated yield of 8,760 kilowatt hours per square meters per year. Depending on the typical values for the annual radiation on planet Earth, the capacity factor can vary therefore from 9% up to 32% in theory. In reality, the capacity factor is also determined by the orientation of the panels, the tilt azimuth, the temperature of the module, system losses, shading, snow, and soiling, and so on. Therefore, the more realistic capacity factor ranges from 10% to 25%. The average aerial power density of PV panels ranges from 22 to 78 watt per square meters. If we consider, for instance, large-scale utility PV, including the spacing between the modules, typical values of 15 to even up to 55 watts per square meters can be obtained. The carbon footprint of a PV system is 14 up to 45 equivalent grams of CO2 per kilowatt hour. It is 34 times less than coal and 20 times less than gas. Depending on the location, the energy payback time of a PV system is 5 up to 17 months. Assuming the currently guaranteed lifetime warranties of 25 years up to 35 years, the energy return of energy investment is 18 to 84 for PV panels. What are the advantages of photovoltaics? Photovoltaics is in many parts of the world the cheapest form of electricity generation. It has a low operation cost, so after installation maintenance costs are minimal because PV systems have no moving parts and typically last more than 25 years. Currently, warranties over 30 and 35 years are given. Photovoltaics is renewable and environmentally friendly as well. Solar energy is an inexhaustible source, we have seen that emits limited amount of greenhouse gases. It secures the energy independence, so users can generate their own power, which reduces dependence on the electricity grid and fluctuating energy prices. It has the highest power surface density of renewable energy technologies. The integration has a high level of versatilities. For instance, PV can be applied at various scales, from small residential rooftop system to large-scale solar parks and integration into vehicles or building integrated photovoltaics, for instance. The challenges are the intermittency. The sun is not shining every day and certainly not at night. So solar energy depends on the weather and the day and night cycle. To guarantee a continuous power supply, battery storage systems are required. Other challenges, like any other renewable technology, is the high initial cost. Currently, the sector is also working hard on finding technological and cost-effective solutions to limit the environmental impact at disposal. So recycling solar panels at the end of their lifetime is complex. So we're looking at new recycling technologies for the old modules, but currently modules are also designed in a circular way. The last one I would like to mention is grid stability. High solar energy penetration can lead to voltage fluctuation and challenges for the electricity grid management. Let's put these numbers in reference to the world's primary power demand, as we have used already 19 terawatts in 2024 in the other video lectures as well. Within this map, we can visualize what surface area is required to cover this demand with the technology discussed in every video. If you consider the total area needed in the form of PV farms and assuming a typical surface power value of 41 watt per square meters, we would need to cover around 0.46 million square kilometers with photovoltaics. This would be 0.09% of the total surface of planet Earth, or 0.3% of all the land area of planet Earth. So we have discussed the important performance metrics of photovoltaics: conversion efficiency, energy yield, capacity factor, aerial power density, CO2 footprint, and the energy payback time. Photovoltaics is a renewable electricity generation technology that has a low cost and low carbon footprint and a high area power density. So let's use all these metrics which we have developed in this course and have applied on hydroelectricity, wind energy and solar energy on some other technologies in the exercises. So see you back in module 3.